Okie dokie, let's rip a few ideal gas exemplars and work out a few of these solutions. So when you're working with ideal gases, you should always consider, like, what are the assumptions that allow us to presume all gases will behave in the ideal manner. And the assumptions generally are that the molecules are small, their individual volume as molecules is irrelevant, meaning it doesn't matter how big they are, and we assume that they have completely elastic collisions, meaning that there's actually no sticky forces among gas molecules. And we know gas molecules have the least amount of sticky force or intermolecular force between them, but there must be some, but we pretend there's none, okay? And for the sake of ideal gases, and the assumption works pretty well. That's why we study it this way. So a couple of realities with ideal gases. We use the ideal gas equation, PV equals nRT. Pressure, as it states here, needs to be in kPa, and volume needs to be in cubic decimeters. N is the number of moles. R is the gas constant, 8.314 joules per mole K. The units of this are specific for the units of everything else. That's why the units really matter here. And then the temperature needs to be in Kelvin. Okay, so it needs to be, if given in Celsius, converted to absolute temperature, which is Kelvin, the temperature in Celsius, plus 273. And then finally, don't forget that you can make a presumption. It's called Avogadro's law, which says that 1 mole of any gas, any ideal gas, at STP, which is 0 degrees Celsius and 100 kPa pressure, will occupy a volume of 22.7 liters. And that's given in the IB data book. So you don't have to memorize that. You just have to remember that that can be a useful shortcut. All right, so we've got one here, a sample of ideal gas at STP. So again, that's 0 Celsius or 273 Kelvin and 100 kPa. If it occupies 16 liters, 16.0 cubic decimeters, what amount of gas is there? Okay, so again, we're looking for what amount. So we're trying to solve for the number of moles, okay? So ultimately, we want to solve for number of moles here. We could just start plowing through PV equals nRT, okay, and solve it that way. We have a temperature. We could convert that to Kelvin. We have a pressure. It is in the correct units, so we've got it. Hang on, I'll start checking these off because that seems like a fun thing to do. We have the pressure. We have the temperature. This is a constant. We have it. It's also in the data book. We're trying to find the moles. Do we have the volume? Yes, we do. It's 16. So we have all these things we could plug and chug and solve for N. There's another way to do it as well, which is using Avogadro's constant. And that's, in my opinion, a little bit easier because it's at STP. Remember, we can assume that at STP, any ideal gas is going to occupy 22.7 liters. Okay, so our constant here, Avogadro's constants, 22.7 liters per mole. All right. So if our final target here is to figure out the moles of gas, all right, how are we going to have to use that constant? We have the 16 cubic decimeters, and we're going to multiply that by the reciprocal of that Avogadro's constant. So we're going to multiply that by, for every mole, it occupies 22.7 cubic decimeters, like that. That'll make the cubic decimeter drop out and render our final answer in the unit of moles. And if you go ahead and do that, it is 0.705 moles of gas. If you go ahead and use the whole ideal gas equation for that, it should give you the same answer. So 6 in one, half a dozen in the other, as they say. Okay, another question. A fixed mass of ideal gas doubles in absolute temperature. So we're going to double its temperature. And it also doubles in pressure. Calculate how the volume is affected. All right, so we are trying to calculate volume here. We're going to have to inevitably play with the ideal gas equation and isolate volume. All right, So let's write out the ideal gas equation, PV equals nRT. Okay, now we have a situation where there's a fixed mass, okay, which basically means that there's also a fixed number of moles, and we're not adding gas to the container, we're not removing gas from the container, we're just going to change its conditions a little bit and then try and evaluate how that impacts the unknown condition of volume. So let's eliminate from this equation things that we know are constant. So we can eliminate the moles because we said it has a fixed mass, and we can eliminate the constant R. So right away our equation is down to PV equals T. We are going to rearrange that and say in situation 1, okay, dividing both sides by T, we had an initial pressure, an initial volume, and an initial temperature. And then because we didn't add or remove gas, the final pressure in V2 and T2 are all going to work like this, okay? So hopefully you can get that far. Now what we need to do is express our final volumes. Sorry, we're not going to be able to do that till the end. Our final temperature and our final pressure in terms of the initial pressures, so we can start dropping variables out of this equation. So if we know that we are doubling the pressure, that means that P2 is equal to 2 times P1. If we know we are also doubling the temperature, that means that T2 is equal to 2 times T1. Okay, so instead of having those terms in, now we can substitute these alternate terms. So I'm going to rewrite this up here in blue. So P1 V1 over T1 is equal to 2P1 times V2 over 2T1. Okay, so I subbed in those two terms. Now we can isolate the final volume V2, rearrange the equation to do that, and then see what happens. All right, so let's isolate V2. So we're going to have to multiply both sides by 2T1. So P1 V1 2T1 on that side. 2T1 will drop out of the right. And then we're going to divide both sides by 2P1. So we're going to have T1 2P1 over here, and everything, all that's left on the right is V2. We've done it. We've isolated our new volume. So we're going to now work out proportionally how the volume is affected. Let's cancel things out of that equation that are redundant. So T1 cancels with T1. P1 cancels with P1. 2 cancels with 2. So what are we left with? We're left with V1 is equal to V2. And lo and behold, what does that mean? It means the volume is not affected. The volume is not affected. Now there are many other ways that you can solve this problem, okay? You don't have to go through this laborious substitution. You might, originally work it out and see that P1 V1 over T is equal to P2 V2 over T, and see, look, if we double the temperature, that is going to have, and since temperature is in the denominator, that's going to have the opposite effect of doubling the pressure, because doubling the pressure is in the numerator, and maybe that makes sense to you, and you can just answer volume's not affected. One way or the other, you get through the finish line here. Okie dokie, and this one, a fixed mass of ideal gas at 1.00 times 10 to the 5 pascals and 20 degrees Celsius is heated up by 20 degrees Celsius in an inflexible container. What is the final pressure? Okay, so once again, we are taking a fixed mass of gas, so that eliminates N from the term. So let's write out the whole ideal gas equation. Once again, we can kind of disregard N and we can disregard R because they're both constants, right? So the important relationship here is that, PV and T. And then we also have this other added bit that it's in an inflexible container. What does that control? Well, that ultimately controls volume. because if the container can't like expand and contract, then the volume of it really can't change, assuming we're not going to break the thing. So we can also knock volume out of the whole process as well. All right, so what this becomes is, again, you could take T on both sides. So you get P over T, P1 over T1 is equal to P2 over T2. All right, so this is what we're going to have to solve, is what is the final pressure. So we're ultimately looking for P2, okay? What we do have, what's T1? Well, the initial temperature, it says, is 20 degrees Celsius. Remember, for all of these problems, anytime we have to put data in and start solving things, we want to make sure it's converted to the proper units. So we're going to convert T1 to Kelvin, right? So if we want to convert to Kelvin, it's temperature in Celsius plus 273. That gives you 293 Kelvin for T1. T2, once we heat the thing up, is going to be, it says it's heated up by 20 degrees Celsius. Well, so now it'll become 40 degrees Celsius, won't it? So 40 plus 273 gives you 313 Kelvin. Then we have our initial pressure. The units of pressure initially given up here are also not in the standard unit that we should use for the ideal gas law. They're in pascals. We need to convert that to kilopascals. So there are 10 to the 3 pascals in every kilopascal. So it goes down to 1.00 times 10 to the 2 kilopascals, which is 100 kilopascals. Okay, so we're at 100 kPa here. So sub that stuff in and solve for P2. So if we're going to isolate P2 in the equation, then we rearrange it. It's going to be P2 is equal to P1 times, so here we go, so 100 times T2, isn't it, on top, 313, divided by 293. Punch that in the calculator, and it will give you around 107 kPa for an answer. Now, you might be able to just keep it in that unit, or maybe it's going to ask you to convert it back to pascals, in which case you would just multiply it by 10 to the 3. All right, hopefully you found this helpful.